All right, welcome back from the break, everyone. It's my pleasure to introduce Judith Ludwig, who will give us the second talk on p-adic geometry.
Thanks for coming back. So my second lecture's title is on the board. We're going to start by introducing some topology on the category of perfected spaces. We're going to then discuss diamonds, and we're going to eventually end up with the Fargues-Fontaine curve. Again, this is a kind of survey talk. There's not much time to go into details. I've tried to focus on the important bits, and let's see how this goes. All right. So yesterday we saw the definition of perfected spaces, and let's just put them all together in a category. So let perf D, perfectoid, be the category of all perfected spaces, okay? And sometimes today we're going to have to focus on characteristic P. So we're going to say perf, without the D, is a category of perfected spaces in characteristic P. So in what follows, there are set theoretic issues, okay? But I will completely ignore them. But they can be fixed. And if you read the literature, for example, if you read the Étale cohomology of diamonds paper, you will see how they're fixed, okay? But I will ignore them. And so I will just tell you about two important topologies on these categories. Namely, first, there's the pro-Étale topology, which I'll define in a minute and say a little bit about, and then there's the so-called V topology, which I'll introduce and say even less about, but still it's going to come up at least in kind of as language, okay? All right. So what's the pro-Étale topology on perfected spaces? Well, let's just first of all define what it means for a map aphanoid perfectoids to be pro-Étale, okay? This is defined as follows. So a map F, and recall aphenoid adic spaces and aphenoid perfected adic spaces. There were these spa of some Huber pair, and if B is perfectoid, then we call it aphenoid perfected space. So if you have a map between B's, then you call it aphenoid perfectoid spaces. You call it aphenoid pro-Étale. If the B arises as a limit of Étale maps, okay? So if this is a limit of AI plus, but you do have to complete, okay? So it's a completed filtered colimit. And these are all demanded to be perfectoid. And the maps from spa AI, and such that all these maps are Étale. Okay, so that's the definition in the aphenoid case. And in general, if you have a map between perfectoids, sorry? Just some filtered colimit of some appropriate set. I don't know. A is fixed, and you're supposed to have maps into AIs such that you can form the limit and such that this is going to be Huh? I don't understand.
It was expression of active.
Oh, thank you. I was okay. I understood sets. So I was like, which sets? Great. So now, yeah, if you take a random map in this category, then it's pro-étal if it's locally on source and target pro-étal. All right. So, okay, this is an abstract definition. Let's see some examples. And this can, well, it tells you in at least two ways. Well, some properties. So if you take a perfected space and you take any profinite set. So this maybe you can write as the inverse limit of some SI. Then you can form a new perfected space, which is denoted by X cross S underlined. And it is just the inverse limit over these spaces, where these are just finitely many copies of your original space. And this there's a natural projection map, and this is pro-étal. Now, if X happens to be a geometric point, meaning if it's sparse COC for some algebraically closed perfected field, then in fact you can show that any pro-étal map will be of this form. So on points, this is just what's going on. Yeah, and in general, these constructions will be immensely helpful whenever you're doing examples. And then the second example, and this is maybe a bit surprising if you've never seen this before, is a Zariski closed immersions. Of affinoid perfected spaces. You see, if you have a SPA RR plus for some perfected algebra R, then you can approach the vanishing locus through rational subdomains, right? You can define open subsets by inequalities, but you can shrink these neighborhoods. And in the limit, you would get a vanishing locus of a function. So, but you're allowed to take this limit, and you know that open immersions are étal by definition. So this is going to give you a pro-étal map. And it tells you that pro-étal morphisms, for example, are not going to be open in general. Okay? All right. And so we can endow all these categories with a pro-étal topology. You can also do it on one perfected space at a time. So there's a small site like that, where you have just any perfected space. And then you take all the perfected spaces above it, which are pro-étal above it. So this map is supposed to be pro-étal from a perfected space. So, yeah, can I finish the sentence? So you can endow any of these categories with a pro-étal site. And for that, I have to tell you what the cover is, and then I'll take your question. So let's look at what the definition of a cover is. So a collection of maps from some yi into some y is going to define you a cover in this pro-étal topology if, well, all of the FIs are pro-étal, And then there's the condition, yeah, what it means to be a cover really. So for all, you want for all U in the target quasi-compact, you want to find a finite subset. And quasi-compact opens UIs in the VIs, in the YIs, such that they cover, okay? This is a finiteness condition that you impose here. And then this defines your topology. Okay, so what's the question?
Example, is this giving these closed spaces like pianos to reduce substitute structure?
If you have like open immersions, I think that's
So is the
oh yeah, I think yeah.
Uniform bring all
Right, yeah, right. Yeah, right. Perfected rings are reduced, so no worries at this point. Okay, so then good facts to know about this are that in this topology, the structure sheaves are going to be sheaves. I mean, the things that we built yesterday. So big O, say, which stands a perfected space to its sections. This is going to be a sheaf. O plus as well. And the topology is subcanonical. Which means that if you have a sheaf which is representable by perfected space, i.e., I'm going to write it out for every X perfected. The assignment Y goes to Hom YX. This is a sheaf. Sheaf. Okay. Right. Can I take the functor of points of what? Well, I don't know. Yeah, let's discuss this later. Right, let me go on. The V topology, I also wanted to introduce. So let me define it briefly now. And yeah, right. It's easy to define actually. So let me do it. So the V topology, and you can only define this on these big categories on perf D and perf. This is defined as follows. So you say a collection Fi from Yi to Y is a cover if actually the same condition as over there holds. So star holds. Let me tell you what star is. So this finiteness condition here. Okay, if you have this condition here, yeah, thank you. Right, and let me put a double star here because I'm going to refer to this as well in a second. Okay. Right, and that's the definition, actually. There's no more condition. So the remark here is, so first of all, yeah, there's no condition on the morphisms. It's very general. If you think of algebraic geometry, then actually, yeah, this condition star maybe reminds you, and this, yeah, this whole thing is considered an analog of the FPQC topology. Okay, so if you go back to algebraic geometry, then you can see parallels there. And it's kind of surprising that this is a workable definition, but it is. And in particular, the fact over there also holds for this. Yeah, so it's going to be a subcanonical topologies, and the structure sheaf and the O plus are both sheaves. Great.
So,
yeah.
So say this is analogous to the FPQC topology
because it's a condition star. I mean,
because like these are morphisms between the vector spaces, and then we look at some algebraic condition, which we look at.
No, I'm saying because there's so little. Because yeah, this is such a general.
The FP stands for like that is part of the FPQC condition. That technical condition that people just forget about, but sometimes we're just keeping the technical part.
Yeah. So that's fine. Okay. So why did I tell you about these topologies? Well, other than I think I was supposed to, it also motivates to talk about the next theme here, which is I want to tell you what a diamond is. And in order to define them and work at all with them, then we need these topologies. So you'll see. Okay, but let me take a moment and motivate why we want to study diamonds. So yesterday, recall we saw the tilting functor. We saw that tilting allowed us to pass from a perfected space in characteristic 0 to a perfected space in characteristic P. Okay, and we saw that this is a really strong bridge. There's no topological information is lost. Yeah, and we also saw at the end, at least very roughly, and so yeah, and maybe more from a classical point of view, we are interested in rigid spaces or in analytic spaces. So over QP. And then we saw, I indicated that one can relate this to a perfected space. Namely, that this Y had a cover by some perfected space. So yeah, you're going to be able to find a protime map where X is perfected. So then, of course, you can relate this X via the tilting formalism to characteristic P, but you can't do it with Y because we can't tilt Y. But maybe, so the question is there a way to relate, and we relate Y to a geometric object in characteristic P in a way that is similar to tilting. So in a way that keeps topological information. But maybe loses, only forgets the structure sheaves, maybe, structure map. Yeah, let me not write that down. Yeah, so maybe the structure map is lost, but just as it was with tilting, but we want to keep topological information. Okay, And the second motivation is that, well, we've seen in other talks the theory of Stuckers, right? And there's a motivation to develop a theory of Stuckers in mixed characteristic, and it has now been achieved. If you want to do this, if you don't yet know this, but want to do this, then the first thing you look at is at the definition of a Stucker, and it really needs the product of spaces. And so if you want to do anything in mixed characteristic, then you would like to form absolute product, at least. Okay, ideally, if something like, I guess, spec Z with itself, but this is not going to work. But so maybe in this non-Archimedean business, you would want to hope, or like you're searching for a way of making sense of the self-product of QP. Yeah, the absolute product of QP with itself, okay? So these are the two motivations. And diamonds are going to provide a solution, or an answer to this. I mean, if we want to work over QP, and I want to build an analog of this definition of a Stucker that we've seen. Yeah, and then maybe the space field is like, maybe you're working over QP.
So wasn't the original one just product over the base field?
No. Yeah, sorry. Is to the X. Yeah, you had like the legs, and this is supposed to give you an analog of. Okay, I'll move on. Yes. Okay, so let me tell you what a diamond is, because we now have all the ingredients to define it, actually. So a diamond is a pro-étale sheaf on the category of perfected spaces in characteristic P, such that it can be written as a quotient where, so X is a perfected space, and R in X cross X, where you write, here you really think of it as a sheaf, and in here you have an equivalence relation. But you want a bit more, such that, this R is also supposed to be a perfected space. And such that the induced maps that you get by projecting on the components, such that the S and T, S and T, so these are maps from R to X. These are the induced maps. These are both pro-étale. Okay, so that's the definition. So let's try and understand this definition. We make some remarks about their properties. So just as diamonds that occur in nature, I guess, here these diamonds also, there are two things: they're hard and they're kind of beautiful. But maybe more mathematically, if you know the definition of an algebraic space, an algebraic geometry, then this should remind you a little bit of it, because algebraic spaces you can define as quotients of schemes by étale equivalence relations, okay? This is kind of similar. And maybe to get more hands on these things, maybe it's sometimes easier to, well, maybe you want to know the following. So if you start off with a pair of perfected spaces and say you have two maps from R to X and they're both pro-étale, then maybe you want to know when you can take the quotient and get a diamond. I mean, yeah, when this fits in this framework, and you can check this. There's a condition. So if you look at the induced map, into the product, then if this is an injection, where you have to be maybe a little bit careful how to define this, but you can check this on points, and really then it means that some map is an injection, then it's actually true, then you can form this, then this is going to give you a diamond. Okay, so yeah, this is maybe more often the situation that you're in. And then this construction actually works. Maybe a couple more remarks. Yeah, I've defined a diamond, or diamonds are defined as a pro-étale sheaf, but actually there are also sheaves for this finer V topology, as it turns out. And so you can use the power of this V topology to study them. So any diamond is a V sheaf. And so, yeah, you can use this to study them. And for example, just to give you an impression of what kind of things are true. So any V sheaf, if you have a V sheaf which injects into a diamond, then it's automatically a diamond. Yeah, so, right. And one more remark, no, two more remarks. So if you have two diamonds, you can form their product sheaf. This is sheaves. And this is going to be, again, a diamond. This is actually not terribly hard to see. You have to check that perfected spaces in characteristic P allow products, and then you have to just check that it's okay with these equivalence relations. And last remark here is that you can attach to any diamond a topological space. And you do it by taking the topological space underlying X and quotienting out by the topological space underlying R. And obviously you have to check that this is well defined. It doesn't depend on the way you write your diamond. But maybe a warning, so it's well defined, but it's not always well behaved. Okay, so these things can be quite tricky. So when you study them, you select a good class of these diamonds. And a good class, well, yeah, I'll tell you why they're good in a minute, or you'll see. So you say that a diamond is good or is spatial, is the term, if it's QC to QS. So I haven't defined what this means, but okay, there's the definition. And if the topological space D admits a basis as a condition of opens U which arise as sub for U in D, quasi-compact open immersion, so subdiamond. Yeah. And it's not high enough. Right. And why are they good? Well, it turns out then if you have a spatial diamond, then its underlying topological space is a spectral space. And we like these, okay? Oops. Okay, so then, yeah. This is supposed to go under there. Okay, so D, in this case of a spatial diamond, then this is a spectral space. And these are well behaved and well studied. Okay, so what I want to do now is just to study one example. Yeah. So I want to take some time to discuss a diamond, which is called SPA-D QP, for reasons we'll see. But let me just construct it and give it the name, and then we'll see what its relation to QP is in a moment, okay? Okay, so let's go back to yesterday. We had two perfected fields floating around, one in characteristic P and one in characteristic 0. And its tilt was exactly this one. And so on it, this is a perfected ring in characteristic P, and on it you have an action of ZP cross. You can write this down explicitly. So gamma of T is 1 plus T to the gamma minus 1, for gamma in ZP cross. And so what you get, if you construct this perfected space, where you just take this product over the, with the profinite set here, then, this action defines you. It's going to define you an action on this space. And so you can look at the associated map, and you can also just take the projection down to SPA QP atomic flat. So one map here is just the projection, and the other one comes from the action. And this defines you this defines an equivalence relation. And so you can take the co-equalizer of this thing and get a diamond. Equalizer. Gives a diamond, which is a quotient of this space. By this equivalence relation, and just to save some notation, let me write it shorter like this. And this is what you call SPA-D QP. Okay, but actually in this business of pro-étale maps, there's also the notion of a pro-étale torsor, and it turns out that this is kind of an instance of a pro-étale torsor. Yeah, so you take, Okay. So why do we call this SPA-D QP? And it's because of the following theorem. So, yeah, the following categories are equivalent. On the one hand, if you look at a perfected space over QP, then, yeah, this is equivalent to a perfected space X in characteristic P together with a structure map to SPA-D QP, equipped with structure map. Okay, so let me actually try and explain this a little bit further, because there are many categories floating around now, and somehow it's just to make sense of all these notions. Right. So if you want to show that these two categories are equivalent, then first thing you do is you consider the following sheaf. Well, first of all, the following assignment, and then I'm claiming things in a minute. So if you look at any perfected space in characteristic P, then you can build a set of its untilled. Okay, so these are pairs where X sharp is a perfected space over QP, and iota is an isomorphism of the tilt of it with X. Yeah, and right, yeah, and it turns out that this assignment defines a pro-étale sheaf on perf. Yeah, and by construction, note, and so does just by definition, the SPA-D QP is also a pro-étale sheaf. So this theorem really tells you now, like, yeah, so this means I can check these equivalences on affinoid perfectoids. Yeah, if you think about it a bit, unraveling what this means, it says that, yeah, if I manage to show that these sheaves are the same, then I've shown the theorem. And so this means you can check the equivalence from the theorem on affinoid perfectoids. And right, so I have to tell you what I'm doing on time. Okay, I'll be, yeah. Let me indicate at least one way. So, yeah, if I give you an untilt, so this is a, yeah, or in other words, it's a perfected space in characteristic 0. Then, yeah, which is an untilt of my X. Yeah, so affinoid perfectoid, sorry, so I fix one. Okay, so this is SPA plus. Right, so if I have an untilt of that, then I want to produce, I should explain to you how to produce a map from its tilt to the diamond, okay? I want to convince you that these two things are the same. So, and you do this as follows, it's a very concrete construction, okay? So what you do is, Well, what you can do is you can take this characteristic 0 perfectoid space, and which lives over a field, but it doesn't live over a perfectoid field. So you base change it to a perfectoid field first of all. So let's look at this thing, which is just the tensor product of R sharp with our favorite characteristic 0 perfectoid field. And you have to complete. And then this is a perfectoid algebra. And you do this a similar thing on the integral rings. Let me not write that down. You take the completion of the integral closure of the R sharp plus in here. And then you can form this perfectoid space. This gives rise to an affinoid perfectoid space. Okay. And what will happen then is, well, the way you've constructed it, it will be pro-étal. There'll be a map to X sharp. And this is going to be pro-étal. There's also going to be an effect because on QP cyclotomic, here you have the Galois action of ZP cross. So this will also inherit this action. And this will be, at the end of the day, a ZP cross torsor. But then its tilt will have the same properties. So, and the tilt here is just a characteristic P perfectoid space, but it lives over the tilt of X, which was of X sharp, which was just X, right? So then this is also same thing. But yeah, you've constructed this perfectoid space over QP cyclotomic, so it has a map to let me go here. So it has a map to the perfectoid field. And so what you end up is, where am I? Right. Okay, yeah. So by construction, I should say, by construction, you have a map to the perfectoid field, QP cyclotomic. And this is CP cross equivariant. By construction, as you're just doing this tensor product. And so you get a diagram. So if you look in characteristic P, the X tilde goes to X. Sorry, no. What I'm doing? To the tilt of this perfectoid field. And this maps down to the diamond by construction, right? Because this was a quotient of it, and it was exactly this ZP cross torsor. And so here you have a map down to X, but because this was equivariant, you actually get an induced map here. And this is what you wanted to produce. All right, so get map. This one, okay. And yeah, the other direction can look up. I don't have time to explain this, but at least maybe it gives you an idea that really this SPADI QP is associated to QP, and it parameterizes untilts. Okay, and so this, yeah. Now I can tell you maybe basically the general story. So similarly, if you have any analytic p-adic space of a QP, then you can attach to it a diamond in a way that is kind of, well, in a way I'm going to write it as follows, but maybe now it makes sense now that we've seen SPADI QP a bit in more detail. So the diamond associated to Y is the following V sheaf. is the V-sheaf of certain untilts that map down to Y. So it's the V-sheaf that is denoted by Y diamond, and it sends a perfectoid space X to untilts of X over Y. So this is perfectoid. And the iota identifies the tilt with X. And maybe you would have quotient out by equivalence untilts, where equivalent, really, if you try to write down what it means, you'll have it. And this turns out to be one of these good diamonds. So this is going to be a locally spatial diamond. And moreover, it has the property that if you look at its associated topological space, then you do recover the topological space of your adic spaces that you started with. So somehow this, if you remember this first motivation that I explained to understand diamonds, this gives you, diamonds indeed give you such a way of going to characteristic P so that you get, you don't lose topological information. Right, and maybe one remark, like two remarks. Well, one remark is in the case where the Y was actually affinoid perfectoid, and you can see, but just by unraveling, so this is SPA RR plus, then by unraveling the definition, you see that Y diamond is representable by the tilt. Yeah, so this really generalizes the tilting construction beyond the case of perfectoid space. And in general, and let me save some time and just tell you that in general, if you want to show this is true, then remember that we had this proposition at the end of last time that you can relate an analytic adic space of a QP to a perfectoid space with this pro-étale cover, and you're using this. This is your X in the definition of a diamond. You're using this to build the diamond, okay, to show that this is okay. And if you then, so you can build this diamond, but if you then want to really understand these extra conditions, you need more theory that is definitely beyond this, the setting of this talk. But maybe one thing. So in the last half an hour, for sure, these untilts have come up a lot, And actually, if you want to show that this is even a V-sheaf, then you really have to get your hands on these untilts. So they've been floating around a lot, but we don't quite, at this point, if you've not seen this theory before, you probably don't really know how to construct them. But there's a way of explicitly actually writing them down, or like more explicitly. So that's what I want to show you next. Yeah, locally, as in, on the topological space. The topological space.
Aha, okay.
Right. So in order. Right, so I want to now tell you a little bit about untilts. And this is motivated by two things. Like if you, for example, look at how this is proved, the fact that this Y diamond is in fact a V sheaf, it'll come up. But then also, if you want to explain the Fargues-Fontaine curve, it's also related. So it's kind of an interlude that is helpful for many things. And maybe even as a separate question. I mean, it's maybe an interesting question to just understand untils. So if you give yourself any Tate ring or factoid, in characteristic P, then then it's a very natural question. Can you actually how can you understand these untils, right? Okay. And so there's a way of parameterizing those, and that I'll just state as a proposition. So what you do is you need to contemplate the ring of Witt vectors. So if you give yourself any perfect algebra in characteristic P, then what you can construct are the ring of Witt vectors. And so this is a ring of Witt vectors. It's a p-adically complete flat ZP algebra. And it satisfies that if you quotient out by P, you get back your original perfect algebra. All right, and so you can use this ring of Witt vectors to parameterize untils. Namely, they're all going to be given as quotients of this ring of Witt vectors. So this ring of Witt vectors is really quite big. If R plus was the ring of integers in a perfected field of characteristic P, then this is this ring also goes by the name A-inf, and it's the kind of fundamental ring that is used in all constructions of p-adic Hodge theoretic rings. Okay, so right. But yeah, let's just look at this general setting. So then, yeah, as I said, you can use this ring of Witt vectors to parameterize untils. So let's take one. Yes, then as it turns out that there's a canonical surjection from the ring of Witt vectors. This map is in the theory often denoted by theta, always denoted by theta. So you can produce a surjection from the ring of Witt vectors down to your untilt, and it's actually explicit. So the ring of Witt vectors can write any element in this form, where these brackets here are the Teichmüller lifts, and you just send this to the Rn sharp p to the n. So okay. If you start with an untilt, you can produce such a map, and the kernel of this map turns out is generated by one element. And you can even say more, it's generated by a non-zero divisor. Oops. Psi, and it has a certain form. And it's always going to be of the form P plus the Teichmüller lift of var pi alpha, and alpha is some element of the Witt vectors. So you can always write it in this form. So this here is a pseudo-uniformizer in R plus R flat plus. No, there's no flat. R plus. Yeah, just the sharp map from yesterday. If you start with an until, then yeah. Sorry? No, I mean, maybe I screwed up. Okay. Okay. So the following theorem due to Fontaine and Cadlaya-Liu is that you actually can, this way, you can get all untils. So there is an equivalence of categories where on the one hand you have perfectoid Haidt Huber pairs SS plus, just general, and on the other hand, you have triples R plus, and then iota or J, where so this here is perfectoid in characteristic P, and the J is in the Witt vectors, is an ideal in the Witt vectors, and it is principal, and this is generated by exactly one of these guys. And we call them primitive in degree 1. By that, I just mean of this form. Okay, so the Witt vectors allow you to get to the untils. That's the upshot here. Yeah, I think so. I mean, non-zero. Oh. All right. So let's get to the Fargues-Fontaine curve. Finally. Okay, and because in the next 2 lectures, we're going to study vector bundles on it eventually. Let me just set things up in the following generality. I'll present you the p-adic version of the Fargues-Fontaine curve, where the starting point is any local field. And I'll stick to characteristic 0 here. And it has, so these are the notations for a uniformizer, and residue field will be FQ. And I'll present you the version, the relative version over an affinoid base. So we start also the second datum that goes into it is the affinoid perfectoid over FQ. I want a map to FQ. And I want to have, I want to fix also a pseudo uniformizer of R inside R plus. Okay, so then in order to define the Fargues-Fontaine curve, let's start with the following ring. Let's look again at Witt vectors. Because I want to keep track of this local field OE, I want to take the ramified Witt vectors, it's called, which is just the tensor product over there. standard with vectors with OE. And I take it as a Huber ring, so I have to tell you what topology to put on, okay? So I want to put on it the topology that's defined by an ideal. And this ideal, I take the pi and var pi generated ideal. So this is the var pi p-adic topology. And this turns it into a Huber ring. Okay. And so I want to look at its associated adic space. So I want to define its associated adic space, but actually, yeah, I don't want to look at the full adic spectrum. Let me just write it down and then say something about it. Let me look at SPA of this ring. And in this ring, you look at two elements, namely the pi and the var pi. So these two guys, they kind of define the topology, right? And so I want to exclude from this full adic spectrum the vanishing locus of these two. Okay. So then it's a proposition. Maybe I'll say a little bit about why this is true. You have to show something here, right? I didn't say, I mean, I said it's not so easy, it's not hard to see that you get a Huber ring. This defines a reasonable topology, but sheafiness is a different question. So you have to argue. But this is actually true that this is an analytic adic space over SPA E as a map down to SPA E. Okay, but by the way, I think it's still an open question that if you're not looking at the smaller thing, the whole thing, that this is a sheafy Huber pair. I think it's in general is not known. But for us, it doesn't matter because we are just interested in this locus anyway. And there you can show that this is an adic space. And you do this as follows. Well, what you can do is, as I said, is an adic space over SPA E. And what you can do is you can take a perfectoid field extension of E and just space change, and then show that you end up with a perfectoid space. And that's actually not too hard to see. And then there's a general theory, a theorem of Kedlaya and Hansen. This is one of these sheafiness properties that if you live under a perfectoid space, if you're superfectoid, then it's actually true that you're sheafy. So this is how you show that this is an analytic adic space. And then yeah. It'll come up. I mean, well, yeah, we want to define the Fargues-Fontaine curve. Let this be the motivation. And we want to have an analytic adic space for sure. And so in these, this is not a Tate ring, the full width vectors. And so we want to invert things. Yeah. So we want to invert at least one of them, and or maybe the second one. Yeah, just. Yeah, for us, the motivation is just want to get to the Fargues-Fontaine curve. But yeah, so given that I have an analytic adic space now over SPA E, and given that we've worked hard to reduce the diamond out of it, then let's look at the associated diamond. And as it turns out, there's an incredibly beautiful and very simple formula for this. Which is this one. So it's the diamond associated to this adic space is just given as the product of the base S, the first ingredient to build this, and the diamond associated to SPA E. And let me see. Yeah. So this lives in the category of pro-étale sheaves. So as pro-étale sheaves. Yeah. Should I say something about the proof? Let me just. Yeah, to like we've studied SPA QP before, and you can do something similar for SPA E, or you just take the diamond associated to SPA E. Yeah, so maybe I'll indicate some things and just like to keep the notation from before and not confuse you. about that. Let's just look at the case where E is QP, and you have an affinoid perfectoid space. Over QP. So this T maybe is given by SPA. When I have so many R's floating around, I'm going to switch back to the Huber notation A now. So yeah, so we've seen before, right? If you have an affinoid perfectoid space over QP, then you're going to get a map from its tilt to SPA-D QP. Okay, so really this is a map to SPA-D QP. So really this is like a section here. And so what I want to tell you is that it's equivalent now. If you start off with a with a T with a map here, it's equivalent to give you a map to this diamond and to give you a map to S, right? That's the content of this now. So then, if you have a map to YS diamond, then this is the same as, well, everything's affinoid, right? So no, sorry, it's to YS first, not diamond, to YS, to the analytic adic space. This is the same as giving a map from the Witt vectors to A plus, but you have like extra conditions such that you want the image of the Teichmuller lift of var pi and P not vanish in A. Okay, so in A, they are invertible. Such that the image of this and this in A are invertible because you land in Y sub S. But then, okay, there's a universal property of these Witt vectors for perfect algebras in characteristic P. So this is going to induce you a map actually from R plus to the tilt here. But this condition here transports so such that the image of var pi is going to be invertible in A flat. But that is exactly the same as giving, the R plus was the ring that was part of the datum for the S up there, right? It's still there. So this is really the same as giving a map to S. S plus to SPA R plus. S is A. Thank you. Tilt here. Yeah, sorry. Right, great, thanks. Okay. Now this is kind of an attempt of a 2-minute explanation of this beautiful formula. Great. And so now let me finish by defining you the Fargues-Fontaine curve. No. So I'll say some general words about once we've defined it. Okay. Sorry. R pi is invertible. Oh, to get the map down there, you want to have if you want to get a map from R to A flat, then this would automatically var pi is invertible in R. You want that to be invertible in A flat. Okay, so on YS, we have an action of the Witt Frobenius. which is defined as follows. So you take an element in your width vectors. That is written as some power series in pi with coefficients Teichmüller lifts of dfi's, and you send it to fi to the q and then pi to the I. And so one shows that this defines an action on y sub s. And it's quite a nice action. It's free and it's properly discontinuous. It's free and it's properly discontinuous. And so you can take the quotient. An action of this cyclic group phi. So the definition of the Fargues-Fontaine curve, and the way I'm writing it is I'm presenting you the p-adic version, and it's relative to the base S. So this is defined as the quotient of ys by this action. There. Because this action is so nice, you can really construct this quotient. It's locally, locally the curve will just look like, I mean, the xs will look like the ys. So given that I've defined the relative thing, this is really not a curve, but it came out of the construction of the original construction. So, but let me make some general remarks that maybe hopefully give you some context. So let me finish this diamond discussion. So as diamonds, then you also have a formula for the associated diamond to xs, which is, you take the formula we had for the ys, and then really the phi just acts on the s here. So this is really just the quotient of phi z cross identity. Second remark is this construction glues. So you can define ys and xs relative to any perfected space over FQ. Right. There's if you're in the case where S is given by a field, there's a scheme theoretic construction, which is historically the first thing that was studied, was constructed. This was historically much earlier. And if you start off with a field and you look, as I said before, you look at this associated ring of width vectors, then this really is the ring A inf that is fundamental to p-adic Hodge theory. And so this curve was kind of invented to understand p-adic Hodge theory from a geometric perspective. So this is this curve is then fundamental to for a geometric understanding of p-adic Hodge theory. And we will learn much more about this in the next two lectures when we study vector bundles on the curve. So this is kind of more, right. And let me just finish by saying why I introduced you today to this object here. it prepares the next 2 lectures, but it is central in the work of Fargues-Fontaine. Because there you want to do geometric Langlands, and for that you have to start off with a kind of, maybe if you want to imitate, you start off with a curve, and it's really, this is the curve. All right, I'll stop here. Thank you very much for your attention.
Thank you very much. Are there any further questions? Yeah.
So you said that it's the speed there, people construct it. How is that?
Yeah, I mean, it would take a few minutes to write it down. You can recover it from the kind of global sections of the, yeah, there's a way of reconstructing it from the p-adic world, but pictures. Yeah, maybe we can discuss this afterwards. I mean, it's quite involved, so yeah.
With kids, can you explain how it helps to study the geometrical access?
Well, at least maybe just, if you know p-adic Hodge theory, then you know that these period rings are very important. And if you want to build them, then really you want to build them from this ring A in. And so this is ring of Witt vectors of maybe this form. So this ring is fundamental to p-adic Hodge theory, and it's fundamental in this construction. So maybe at least this gives you an idea that there's a link. Okay, but then yeah, vector bundles on this curve will be, you will be able to interpret using yeah, things from p-adic Hodge theory as well. So I have to be very vague here because we haven't built what we need to see this, but